Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is lecture video 16, and we are in lecture 6, part 1, in the section for MLE and MME. So far we have completed our discussion of the likelihood and MLE, how to find it with the likelihood function and the log likelihood function. And in this video, we're going to talk about the invariance property of the MLE and unbiased estimators. So why don't we go ahead and get started. So if you recall, for the normal distribution with mean mu and variance sigma squared, we called this theta 1 last time and this theta 2, we found that the maximum likelihood estimator for mu is x bar, and for sigma squared, it's 1 over n sum of xi minus x bar quantity squared. To do this, we had to solve a system of two equations with two unknowns, and that's because we had two parameters. If we have three parameters, then we'd have three equations and three unknowns, and then we might want to consider using a matrix or some other nice system to solve for the parameter values. Okay, so we had to solve these two differential equations. So we took the derivative of the log likelihood with respect to theta 1, set it equal to 0, and we took the derivative of the log likelihood with respect to theta 2 and set that equal to 0, and then we solved. Okay? So now we're going to talk about a property that makes finding new MLE a lot easier. So let's say that theta hat's the MLE of theta, a population parameter, and this is based on a random sample from the distribution with a PMF or PDF that's f of x and theta. Now, random sample is actually assumed in this class, but because it's the only case we're dealing with. But remember, if you go to grad school and you get an advanced class, they may introduce at some point non-identical or non-independent methods here. So those do exist. So make sure you remember that this invariance property is for a IID random variables or a random sample. Let's say that we have g, and g has to be a one-to-one function of theta. Then g of theta hat is the MLE of g of theta. So g of theta is a function, and we want to know the MLE of this function of theta, then that's going to be g of theta hat. So that makes it very easy to find. Once we find the MLE of theta, we just take the function of it, and we get the MLE of the function of theta. Okay, so let's prove this. So we're going to let phi equals g of theta denote the new parameter of interest. And sigma of phi, which is equal to phi, which is equal to g of theta, such that, so it's a set of that, such that theta is in sigma. So that's our new parameter space of interest. Okay, and then we have let theta equal h of phi, which is equal to g inverse of phi. So h is the inverse function, so that we don't have to write the -1, we can call it h. Then we have L of theta is equal to L of h of phi. So h of phi here is theta. So we substituted in for theta with h of phi. And we can say because L of theta is maximized over sigma of phi, whoops, not over, over sigma of phi when h of phi h of phi equals theta hat equals G inverse of phi, right? Okay. Therefore, phi hat, or phi hat must satisfy the equation H of phi hat equals theta hat if and only if phi hat equals H inverse of phi, which is equal to G of phi. Okay? And that proves it. Okay? So we end up with phi of hat is equal to H inverse. So this is true, and if we take the inverse of both sides, or that we take H of both sides of this, or all three parts of the equality, then we end up with H of phi of hat equals theta hat. Okay? And we have that theta hat is equal to H of phi of hat. So this simply but effectively and logically shows it, okay? Shows the proof. So make sure you study this step by step and that you understand the logic of how this all works. If you don't, you need to review it until you do, because I may throw a similar type of proof on the test, okay? So that is our proof for that. Now we're going to move into something called unbiased estimators. So we have this statistic theta hat. So in this section we've used theta hat as an MLE, but in general theta hat is simply an estimate of theta. So now we're not talking about a MLE, so to speak, and that's why personally I like to write MLE here, so that we know that it's clear that we're talking about an MLE. Again, if there's a subscript already there, it makes it messy. Oops, wrong button. Okay, so we have this statistic. It could be any estimator of theta, but we're going to say that it's unbiased if the expected value of theta hat is equal to theta. So let me define bias. Bias of theta hat is equal to E of theta hat minus theta. This is the definition of bias, and you need to know this, so please put this on your formula sheet. Okay, so let x1, x2, x3, x4 be a random sample from a uniform distribution. F of x and theta equals 1 over theta, where x is greater than 0 and less than or equal to theta. So we're going to let y1, y2, y3, and y4 be the order statistics. And then sigma is the set of theta such that theta is between 0 and infinity. Okay? So theta is just positive in this case. All right? So we don't want any negative values for theta. We're just going to stay in the positive half of the number line. So the first thing is find the MLE. And so because of this, because we're using this as just an unbiased estimator and we're not specifying this in MLE, I am using the subscript just to make sure that it's clear. Okay, so the first thing we need to do is we need to find L of theta, which is equal to the product of f of x I theta, which is equal to the product from I equals 1 to n of 1 over theta. Okay, so that's the PDF or PMF. Yeah, PDF, it's continuous. And so this is going to be 1 over theta to the 4th. Oh, n is 4, so I need to make sure that I put in that n is 4, not n. Oops. change back to this, 4, 4. So there's 4 of these, so we need 1 over theta to the 4th. That's our joint PDF. It's also our likelihood function of theta. And so we need to put in there that theta is xi, so theta is greater than or equal to xi and less than infinity. Okay? And we could also state that xi is positive. So we don't need that if we've got these. So we could state that and make sure that we have it fully defined here. Okay? So in order to maximize L of theta, this we don't need to use much. We can just look at this function. To maximize L of theta, we need to do what to theta? Well, 1 over theta to a power. The bigger theta is, the smaller this value is. So the bigger theta gets, the smaller L gets. So the smaller theta gets, the bigger L gets. So we need to minimize theta. Okay? Now, to do this, notice that theta is greater than or equal to xi for I equals 1, 2, 3, and 4. Hence, the minimum of theta is theta hat, and we'll call it MLE, equal to, which is the maximum of xi. It can't be, it has to be bigger than all xi. It has to be bigger, I should do that here. Theta has to be bigger than all xi. What's the largest xi? Well, it's going to be y4. The maximum value of xi is the largest order statistic here. So this is going to equal y4. So therefore, theta hat MLE is equal to y4, the maximum or the largest order statistic, the max of x, or the fourth order statistic, since there's 4 random variables. So that was A. B, determine if theta hat MLE is biased or unbiased. Okay, so first, if f of x and theta is equal to 1 over theta, recall that f of x theta is equal to the integral of f of x theta dx, in this case from 0 to theta, right? And, well, yeah, 0 to, okay, so I always forget this the first time. So this needs to be x, and we need to change x to a different variable so that it's not confusing. So we'll change that to t. Okay, so that's the definition. If we do this, we're going to get x over theta, because there's no x here. We take the integral of this with respect to x, we get x times that constant. So we have x over theta, where again, x is between 0 and theta. That doesn't change, but it can be equal to theta. All right, so now, if, by the way, up here, if we didn't have the equal to sign here, we would have to take something called the supremum. If you remember that from calculus, I don't know if you do or took advanced calculus. So it wouldn't be y4, because if x can't equal, if theta can't equal x, then theta hat can't be y4. It has to be the max, it has to be the limit of the max of xi if it can't be. So, or the limit of something. So it would have to be something we call the supremum, okay? Now, so we have f of x, the CDF, okay? And the PDF of y4, which is equal to theta hat MLE, okay, is, if you recall from the section on order statistics from last semester, it's going to be G4 of Y4, okay, which is equal to N times the CDF of Y4 raised to N minus 1 F of Y 4. Okay, and we have that 0, let's see, oh, I have room. And so we have 0 is less than, less than y4 is less than or equal to theta. All right, so we substituted that in where x was. And so we have this, and so, oh, I didn't work it out, so I need to work it out before I put this, which is equal to what? So we're going to substitute in. N is 4, F is x over theta, and it's raised to the N minus 4, so x, but we're going to substitute in for, it's not f of x, it's f of y, so we're going to, y4, so we're going to have y4 over theta. Oh, I need to make that easier to see. And this is raised to the N minus 1, which is 3. And then we have f of y, which is simply 1 over theta, y4. There's no y in the PDF. So this is equal to, if we solve it out, 4y4 cubed over theta to the 4th. And now we can say 0 y4 theta. There we go. So this is our PDF of y4. So we need that in order to do the expected value. So we need the expected value of y4, which is equal to the integral of y4 f, or we're calling it g4, g4 of y4 dy4, and this will be from 0 to theta because it's over the whole range. And so we need to substitute in, so this is going to be the integral from 0 to theta of y4 times 4y4 over theta to the 4th dy4. And this is equal to, we have 4y4 to the, oh, I missed the cube here. So it's going to be to the 4th over theta to the 4th dy sub 4. Okay? And when we take the integral of this with respect to y4, we raise the exponent 1 and divide by that same number. So we end up with 4 y to the 4th, y sub 4 to the 5th over 5 theta to the 4th. Okay? And so we can, so y, and we're going from 0 to theta. So this is 0 to theta. And so we substitute in. If we substitute in 0, we get 0. And so we're going to end up with 4 theta to the 5th divided by 5 theta to the 4th, which is equal to 4/5 theta. Okay? This is not equal to theta. Therefore, theta hat MLE is biased. Okay. Now, C, find an unbiased estimator of for the let's see, what does it say? Find an unbiased estimator for theta. Okay, we're going to use the invariance property. By the invariance property, so now we get to the example. So by the invariance property, G of theta hat equals 5/4 y to the 4 is unbiased. So 5/4, how did I get that? So I had that we had 4/5 theta equals E of y4, right? Okay. So, or actually y4, I'm sorry. If we set this equal to y4, solve for theta. This is true if theta equals 5/4 y4. And this is how we're using the invariance property here. So make sure you show this. Okay, so that's all for this video. If it's applicable, make sure that you update your formula sheet or your list of definitions, your list of distributions. But as always, if you have questions, please come to virtual office hours. I'm happy to help you. If you can't wait, if you need help before then by all means email me and I will get back to you as soon as possible. Until then, please take care of yourself and we'll see you next time.